This is a pre-recording of a talk to be given at the 4th International Conference on Recent Advances in Physics on the 24th and 25th of October in Dubai. The paper title is The Unification of Physics, and the paper covers an approach to the fundamental nature of matter, starting from the point of view of general relativity and space-time, rather than starting from the point of view of quantum mechanics. The general relativity, the Einstein equations of general relativity, apply very well on the large scale. So it's a good starting point for finding a solution with general applicability to the large scale and the small scale. Deducing the structure of the atom has always proved difficult because you only get very macroscopic clues seen dimly through experiment, and you can only begin to piece together a picture of what's going on only by guessing at what the fundamental nature of things could be, and then seeing if your guess really makes sense in terms of experiment and observation. So let's start along this process. And in starting, we need to think about the nature of light, because ever since James Clerk Maxwell discovered that the speed of light and the speed of electromagnetic waves was the same, it became clear that light and electromagnetic waves were part of one spectrum. But Maxwell realized that for there to be a wave, something must be waving, and he wasn't clear, he definitely didn't think that the field was the medium for transmission of light, and at the time they were still looking for the ether. So let's progress to slide 1, and we start with looking at a recent observation. LIGO has been looking at detecting gravitational waves, and the first detection was of a black hole merger, which didn't produce any additional radiation. But once you get to a neutron star merger, you not only get the gravitational waves, but you also get the radiation, gamma rays and subsequently light rays, coming from the same event. And what was observed is that the gravitational waves came through, but the speed of the gamma rays and the light rays through space was exactly the same. So you might think, well, this is no surprise. We all know that gravitational waves travel at the speed of light. We've known that ever since the general relativity equations were written down. So why the puzzle? Well, the puzzle is that current theories of the transmission of light suggest that it's a perturbation of the electromagnetic field. And if we assume that the electromagnetic field is independent of space-time, and realizing that the light and waves have come across a distance of 130 million light years, and we know that space-time is expanding, and at that distance, the recession velocity of this event would be about 1% of the speed of light. And that means that the the expansion, which we know affects the gravitational waves, because the gravitational waves are definitely waves propagating as a disturbance of space-time. So if the electromagnetic field were completely independent of space-time, we wouldn't expect them to arrive at the same time. And this strongly suggests that the propagation of light is as a wave disturbance of space-time. So space-time is the medium for the transmission of light. So when we look at the hydrogen atom, we can see in this diagram here, we have the nucleus, and we have a change of state being depicted here. The electron is in an outer shell, and the looped wave moves closer to the nucleus and loses energy in the form of a photon. And this then suggests that we should consider the electron to be a looped wave in space-time. And that is the thesis of the space-time wave theory, that when the electron, which is a looped wave in space-time, moves to a definite energy state, it releases a linear wave, a straight line, not looped wave in space-time, which is the photon. So where do electrons come from? A neutron decays into a proton and an electron, and we've deduced that the electron is a looped wave in space-time. So this then strongly suggests that we should think of the neutron and the proton as a looped wave in space-time. And all of these looped waves are looped waves traveling at speed c, at the speed of light in the loop. And they all follow the rule that the energy, or in case of loop waves, the equivalent mass, is equal to Planck's constant h times the frequency. Now, for the proton and the neutron, how many wavelengths are in the loop? Well, we can actually work this out by taking the mass of the proton that we know. We can work out the energy using E equals mc squared. We can then work out the frequency using E equals hf. And of course, we can then directly get the wavelength. And then we know approximately the radius of the proton because we can measure the charge radius. And the charge radius is going to be, well, at the outer limit of the proton as measured, as shown in this diagram. So then we can say, well, x times the wavelength has got to be equal to 2 pi r, where r is the effective radius. So in this diagram, I think you can see a circle labeled 0.6. Well, that would be where we're talking about the effective radius being. It's the kind of center point of the null point of the sine wave. What you get from this is the conclusion that the proton and the neutron are 3 wavelengths. So now we've come to the conclusion that all matter is made up of waves looped in space-time. And so we can start to reflect on the implications of this in slide 5. You can see we have a number of looped waves, and these are waves of space-time curvature. And you can see that at a distance from these waves, we would feel the effect of these curved space-time entities, and the effect is additive. We know from general relativity that the gravitational effect of mass is additive. So what this is saying is that these small, tiny curved space entities, when they accumulate in their effect, they have an effect at a distance, a very small effect. Gravity is relatively a weak force, but they have an effect. And you can see from this slide an explanation of how mass curves space-time. General relativity asserts that mass curves space-time. This explains how it does it. And in slide 6, looped waves respond to a curved space environment. You can see here we're looking at the Earth's surface, which implies then a gravitational field. And the looped waves in space-time, you can think of them as almost like little gravitational field sensors. They are, the wave energy is traveling in the loop, and it senses that the energy in one position is greater than the energy in a different position, closer, and as a result, there is an acceleration towards the huge mass of the Earth's surface. So this explains why mass responds to space-time curvature. So when you take general relativity and the space-time wave theory together, this completely explains the property mass. There is no need for any field explanation, any Higgs field explanation, for example, to explain the property mass. We've got it covered, both inertial mass and gravitational mass. Slide 7, the dual slit experiment. In this experiment, it's always a good indication of the descriptive nature of a theory. So if you want to look at the Copenhagen interpretation or the many worlds interpretation of quantum mechanics, use the dual slit experiment, because it brings to life exactly what the background description is for the theory. So I'm going to describe the dual slit experiment in terms of the space-time wave theory. So we have on the left of the picture a light source, and a single photon is emitted from this light source, which then passes through both slits. And remember, we're talking about a real physical wave, which then undergoes interference because it's passed through both slits. We've got maximum and minima coming from each of the slits in the apparatus. And the photon wave arrives at the detector screen. Now, we have to look at the detector screen, and if, for example, this were a photographic paper, then there is only one atom of the detector screen with an outer electron which is going to absorb that incoming photon. So what's happening at the point of detection is that the entire photon, which is spread out over a distance of some centimeters, is suddenly drawn in and absorbed by that atomic electron. So you can see that the detector is playing an active role. It's not like the photon wave has collapsed to a particle and then hit the screen. No, that's not what we're talking about. We're talking about the wave being drawn in by one point of the screen. And this solves the measurement problem of quantum mechanics, which is related to the problem of the collapse of the wave function. So when we look at the hydrogen atom, we can compare the Copenhagen interpretation with the space-time wave theory description. And in the Copenhagen interpretation, you have the concept of a point particle with mass m and momentum p, and it exists with a probability distribution. And then if you just look at the space-time wave theory description, you have this looped wave, which is the electron, which wraps around the nucleus many times before the loop is closed. And you can think of the path of the wave as being the equivalent of the track of the particle in the Copenhagen interpretation. Except that in the space-time wave theory description, the momentum is spread out over the entire length of the wave. This equivalence, this description, means that we can see that the equivalence will lead to the Schrödinger equation of quantum mechanics applying equally well to the space-time wave theory description, because we're saying that the momentum, even though it's spread out, is equivalent. So in that case, we can see that we have good reason to believe that in the space-time wave theory, the Schrödinger equation applies. And this is a good thing. It's a very good thing, because that tells us a lot about the fundamental structure of things, and it's proved very accurate and useful. All we're doing is replacing one underlying description that goes below the Schrödinger equation for another one. Slide 9, electric charge. So we've talked about space-time waves, and we're getting familiar with space waves. In gravitational waves are a perturbation of space coming from millions of light years away through space. But how about the time dimension? And what is being illustrated here is that the wave in the space dimensions is affected by a wave variation in the time dimension. Now, general relativity tells us that in the time dimension, we can have a variation in the rate of passage of time at the macroscopic scale. So it's not, variation in the rate of passage of time is not a new concept. It's just that we're applying it at the very small scale of particularly the electron and the proton. So what you can see in these diagrams, and you think of the passage of the space wave as causing the expansion and compression of space. If you extend the time period for the expansion phase and reduce the time period for the compression phase, then you get a result which is a net expansion. And if you have the variation in the time dimension 180 degrees out of phase, then you get a net compression. And I can't tell you which one corresponds to positive charge and which one corresponds to negative charge. But what is clear is that if you had two waves with net expansion, then they will be in a lower energy state if moved apart. And with net compression, they will find a lower energy state if moved apart as well, if they're both of the same charge. And if they're opposite charges, such as an electron and a positron, they will find a lower energy state if moved closer together. So now we come on to the question of electron spin in slide 10. Now, the diagram shows this experiment. A furnace creates a beam of silver atoms. They pass through an inhomogeneous magnetic field, and experiment shows that the silver atoms are moved upwards or downwards, depending on some property of the silver atom, which is termed spin. Now, silver is a very good choice for this experiment because if you remember, the outer outer shell of the silver atom has just one electron. So we can think of the silver atom as containing a nucleus and a number of inner shells which are filled, and an outer shell which is occupying a shell which gives it great freedom of movement. And so what happens is that this outer electron is in a random orientation. We're looking at slide 11 now. And after it enters the magnetic field, the electron is going to be oriented by the magnetic field into one of two states. You can see on the right-hand side, you've got one of two possibilities, which you could describe as clockwise or anti-clockwise. And this creates a magnetic dipole. And so this magnetic dipole will either have north-south orientation one way or the other. And that difference will cause the silver atom to physically move up or down. And this explanation, to me, is a much more satisfactory explanation going down to the true nature of things, rather than thinking of the spin as being a quantum superposition of up and down. the core theory equation proposed, you might recognize this as the Einstein equations without the cosmological constant. And these equations, basically what I'm saying is that where we've been searching for a core theory of everything, this is it. We just need to figure out exactly how this equation is applied at the small scale, because at the small scale, you can see illustrated there a looped wave in space-time, which is a neutron in this case. And given that this is a looped wave in space-time, it would seem entirely appropriate to use an equation to model it, which is all about relating space-time curvature to mass-energy distribution. So, given this proposal for the core theory equation, there is clearly a lot of analytical work to be done to apply this equation to model the looped wave. And this is not at all straightforward, because when you model, for example, a neutron star merger, you've got a pretty good idea of the distribution of mass that you're starting with. But even then, as I understand it, you don't get an exact solution to the equations. You have to use the equations to model on a perturbation basis exactly what the current state would lead to in terms of the next state. And this is the kind of approach that would be needed. You'd have to basically guess at the detailed structure of the looped wave, and then use general relativity equation, this core theory equation, to see the evolution of that wave. And you'll know that you've got the right answer when you find that you've got a stable looped wave of 3 wavelengths, where the energy times the wavelength is equal to a number, and that number is equal to Planck's constant times c. So here we are illustrating the neutron in a slightly different way. You remember we talked about the nature of electric charge as being a wave in space-time of compression and expansion. So we can think then of the neutron as being a neutral particle, but actually think of the compression and expansion as representing a positive and a negative charge as the loop of 3 wavelengths travels at speed c. So you can see that if you had 2 neutrons with a shared axis of rotation in close proximity, then they would bond, negative to negative, negative to positive, and positive to negative. And so one could imagine once a dineutron is formed, it will be very stable. And this dineutron is the proposed dark matter particle, which we're all looking for. Finally, no discussion of unification would be complete without thinking about the fundamental forces of nature. And what this contribution, what this chart is saying basically is that when we're looking for why there are 4 fundamental forces and how they have a common theme, the answer is really that the concept of force itself is not fundamental. We've known for some time that the gravitational force is not really a force. It's a result of space-time curvature. And generalizing that, all of the fundamental forces are not really a force. They're just the result of the possible positions of objects in space-time having an energy difference. And so each force depends on the context in which it occurs. So that concludes the presentation, and this has been prepared partly as a dry run for me and partly as a precaution in case I'm unable to present at the conference.